Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using, as far as possible, only the standard libraries and the SDL2 library to allow us to display results in a window. In the previous episode, which was episode 10, we looked at how to implement refractive material, so we could do glass, water, that kind of material for our objects. If you haven't seen that, go and check it out. There's a link in the description below. And I also said that that would be the end of that part of the series, which it was. I think that makes quite a nice self-contained 10-part series on the basics of ray tracing and how to implement those in C++. What I'm doing from now onwards is going to a more devlog style of videos, and really just sort of want to continue to explore increasingly advanced concepts. So I've got all sorts of ideas of things that I want to do. I want to ultimately go on to look at physical-based rendering or PBR and path tracing and that kind of stuff. So if that sounds interesting, make sure you've subscribed so you don't miss those videos when they come up. Anyway, the episode today, what I wanted to look at is fixing a slight problem that I overlooked with the way that we calculate the normals. Now, if you recall, we are using geometric transforms so that when we cast a ray into our scene, when we test for intersections between that ray and any object, we first transform that ray back into the object's local coordinate system and then test for intersections. And the great advantage of doing that is it makes it very easy to implement more complicated objects. And of course we can apply uneven scaling and that sort of thing, so we can take a sphere and we can squash it and we can do all of that kind of stuff, which is kind of cool. One thing that I overlooked when I wrote that code originally is that actually the way you apply those transforms to the normal vectors, to the surface normals for the objects, has to be slightly different to how you apply the transform to the actual object itself and indeed to the rays cast into the scene. And that's what we're going to look at today. So this is probably going to be a shorter video than most in my series so far. Well, we'll see about that, but I think it should be. But hopefully that will be of interest. Anyway, if you do like this video, please do hit that like button. It does help a lot with the YouTube algorithm. And if you haven't subscribed to my channel, please consider doing so that you don't have to miss any future videos. Thank you very much. Anyway, right, let's jump into it. Let's have a look first of all at a little bit of the theory of exactly why this situation occurs and why we have to use different transforms for the normals compared to the actual surface of the objects. Okay, let's go. Okay, so I really wanted to start the video today just having a quick look at exactly what's going on. So I've said that there's a problem with the normals, so let's start by actually looking at that. In this case we have a sphere, a ball, mathematically called a ball, of course, in blue, and I've highlighted a number of points on the surface of the sphere with the yellow points that you can see there, and then I've plotted the normals to the sphere, the normals on the surface of the sphere at those points in the orange arrows. Now what you can't see here is there are also some green arrows which show the normals calculated in the way I did it originally by applying the object transform the original way, and the orange arrows show the result of applying the transform correctly, which we're going to come to have a look at in a moment. Now, when the transforms are completely uniform, so we have uniform scaling, and this is it. So this is a unit sphere at the origin. There's nothing fancy going on. Everything is fine. See, these are very clearly the correct normals, both orange and green. But the interesting situation comes when we start to apply something such as an uneven scaling. So if we do that, we can see as we squash our sphere, so in this case I'm expanding the sphere in the x and y axes but leaving it fixed in z, and we can see that we very rapidly get quite a large degree of divergence between the orange and the green arrows. By the time we get to here, we see that the surface, the normals to this surface around the middle, which is roughly where we are, should be pointing pretty much vertically upwards, which the orange arrows are, but we see the green arrows have diverged significantly. Okay, so if we go back the other way, so go back to our uniform sphere, you can see that as we do that, the arrows come back and they converge again. And indeed, if we go the other way, if we squash the sphere in the other direction, we see that we get exactly the same effect. So there I'm simply scaling the sphere making it smaller in x and y but leaving it in z. And we can see the orange arrows again represent what we would expect, the green arrows being the arrows, the normals that have been transformed using the same scaling, same transformation strategy that we apply to the object, clearly diverge. Now, it's worth bearing in mind that in actual situations, the effect of this is really very small. And that's because most of the time we're not applying extremely uneven scalings and that kind of thing to our objects. Where it does show up is if you're doing cones and you want to make a stretched cone. But again, because in reality you're not going to stretch it all that much, the difference is really very small. However, I'm a great believer in getting things right, and I think, there may well be situations where we want to do very squashed or elongated objects, and just generally it's, I think, quite important that we get this right. The one thing that I want to look at is, what's interesting about this is why they are different. Why is it that we can't simply take the transform that we use for the surface of the object and apply it to the normals? And first of all, just to show that, we should look at what happens when we compare a normal vector to a tangential vector. So in this situation, we have the same unit sphere at the origin here in the middle, and we have a point of intersection marked on that sphere in yellow, and then we have the normal vector as before in orange, and this time the green vector shows the tangent of the surface at the point of the yellow sphere. So the green arrow is a vector that is tangential to the surface of the sphere at the point highlighted in yellow. And what's very interesting is if we apply the uneven scaling as we did before, now in this case I'm only using the original method to transform the vectors, and you can see that whilst the normal vector very clearly becomes distorted, it's no longer what it should be. It should of course be pointing more vertically here. You see that the tangential vector remains correct. It has followed the surface and it's still tangential to the surface. If we look at that situation again, so again starting with the unit sphere, and this time we're going to transform the normal using the new method that we're going to look at in a moment, we see now that we get exactly what we would expect. So this is the result we should expect. The normal vector becomes increasingly vertical because of the shape, the change in shape of the surface, and the tangential vector remains exactly the same. Okay, so this explains a little bit of why this difference occurs. So vectors that are tangential to the surface are transformed correctly by the transformation, and vectors that are perpendicular to the surface are not. And actually, if you think about that conceptually, that kind of makes sense, because a perpendicular vector is, well, it's perpendicular to the surface, so you don't necessarily expect it to transform the same way. And likewise, if you think about squashing a surface, if you define the vector for the normal simply as a point away from the surface, when you squash it, that point is going to get closer, where in reality, actually, you want it to get further away. So you could sketch that out on paper if you don't believe me, but you should see what I mean. Anyway, let's have a look at the maths of exactly what's going on, and then we're going to go on to have a look at how we can actually implement this in our code. This is where we were with the previous episode when we originally looked at the geometrical transforms. So go back and check out that episode if you haven't seen it, if this doesn't make any sense to you. That offers quite a good explanation of everything that's going on. What we looked at then is we found that we could combine all of the different transforms together into one transform matrix. And to do that, we had to make our transform matrix 4 by 4, even though we're dealing with three-dimensional vectors. And that was so that we could include the non-linear component of the transform that's given by the transformation, by the translation tx, ty, and tz. So what we ended up with was we have a matrix here for the scaling, a scale in x, y, and z, and then we have our matrix here for the translation component, tx, ty, tz, and then we have our three matrices for rotation about the x, y, and z axes respectively. And what we found is that we can combine all of those together simply by multiplying them to give one single transform matrix A, which is 4 by 4, that we can then apply to our vectors in order to give the transformed vector, or we can invert that and do the transformation in the other direction. Okay, bearing in mind that it's 4 by 4. Now, the interesting thing is we end up with a matrix that looks something like this. So we have this component here of A11 through to A33. Now this is known as the linear component of the transform, and then we have our translation here, tx, ty, tz, which is the non-linear component, okay, and then the bottom row is a 0, 0, 1. Okay, so tx, ty, tz represent the translation component, whilst A11 through to A33 represent the linear component. So Actually, to transform a normal vector, we're only really interested in the linear component. If you think about it, we do not need to worry about the translation tx, ty, and tz. And in the code that I wrote before, I actually wrote in a code, because I didn't do it this way, I used the full 4x4 transform matrix to transform the normals, and so I did some little bit of vector arithmetic to account for the translation, and it did indeed work. But of course, as we've seen, where it doesn't work is when we want to actually apply some kind of uneven scaling. But if we extract the linear component, which we're going to call a-lin, containing just the elements a11 through to a33, such as this, we can then actually use that to transform any vectors we like. What we've seen is that any vector that's tangential to the object surface can be transformed simply by multiplying it by a-lin, okay? And that will give our transform tangent, okay? And t there is the tangential vector. But to transform a normal vector, we know that we need something else. We've seen that it doesn't work if we just apply a-lin, or a, so we need something else. So we're going to define a new matrix called B, and we know that we need to our normal transform, the vector n hat, is going to be equal to b multiplied by the vector n, and we need to find b. So we know that n hat must be perpendicular to the transform tangent t hat, okay? In other words, b multiplied by the vector n, you see here, must be perpendicular to the linear transform a-lin multiplied by the vector t. This can only be true if the dot product of b times n and a-lin times t is equal to 0. And that's exactly the same as requiring that the transpose of b times n multiplied by a-lin times t is equal to 0. And we can satisfy that condition by requiring that the transpose of b multiplied by a-lin is equal to I, where I is the identity matrix. And then, of course, we can rearrange that. So we can take b transpose a-lin equals I. We can rearrange that to be the b transpose is equal to I times the inverse of a-lin, which then gives us that b is equal to the transpose of I times the inverse of a-lin. And, of course, the identity matrix times by any matrix is simply the matrix that you began with, so that is simply a-lin to the -1 transpose. So to transform the normal vector, we extract the linear portion of the transform a-lin, we find its inverse, a-lin to the -1, and then we transpose that to give the final 3x3 transform matrix a-lin to the -1, all transpose. Okay, and that is actually what we have to do. So what we're going to do is modify our code to do that. So we're going to extract the linear portion of the transform that we're using, and then we're going to take the inverse of that, and then we're going to transpose it, and then that's what we're going to use to transform our normal vectors. And that does indeed give then the right result. As we saw, that gives us the orange arrows that we saw in the illustrations at the beginning. Okay, so let's jump in and have a look at how we can actually do that in code. Okay, so to begin with, I'm looking at Gtfn.hpp and Gtfn.cpp. These are the implementation and definition of the class that we wrote to handle the geometric transforms back in that particular episode. And what we need to do is we need to add a couple of functions first of all to this. So we need a function here which returns a type of QB vector double, and I've called it apply norm. So the purpose of this is to apply the transformation to a normal vector, and it accepts as input simply a const QB vector double reference to input vector, okay? And I've also added a function to return the normal transform should we want it as a 3x3 matrix, okay? And we have one private function here, which I'll call void extract linear transform, okay? So those are the changes that we're making to Gtfn.hpp. Let's jump over and look at Gtfn.cpp. Okay, so here we are in the CPP file. I want to just first look at the function to extract the linear portion. Okay, so I've created this function here, void qbrt : gtform : extract linear transform. And this is really very simple. All it does is copy the linear portion out of the forward transform. Okay, so that's very important. We have both forward and backward transforms defined. We're only interested in the forward one here. So we create this new variable here called m_lin tfm for linear transform, which was actually defined in the header. I didn't mention that. It's a type, it's QB matrix 2 type double 3x3, and then we set element ij, and we simply grab the corresponding element out of m_forward transform like that, and we're just using a simple loop to loop over the 3x3. Okay, that's pretty straightforward. And then we take the inverse of that, and then we transpose it, and that is then the linear transform that we want to use when we apply to any normals. Okay, and we have also the function to return it. It's really very simple, just returns m_lin tfm. Now, what we do then is everywhere where we define or modify the transform, so for example in the constructor, this is the most used use case for this class, we call the set transform function that actually sets the transform, and then we call extract linear transform that then calls that function we just looked at to actually extract the linear transform that we can use for processing normals. And that's a good way to do it, so that whenever we set up the instance of Gtfn, we're predefining it, it pre-calculates everything, so we don't need to be doing that every time we cast array or anything like that, which would obviously be hugely inefficient. The last function I want to mention in the Gtfn class is apply norm. So we just saw in the function definition that this accepts as input a reference, a const reference to a QB vector double, and very simply we just have result is equal to m lin tfm multiplied by input vector and return the result. It's really as simple as that. Okay, and that's basically it for Gtfn. Okay, it's really very, very straightforward to implement. So let's have a look at actually how we do this in the code for each individual primitive object. Okay, so starting with spheres, so object sphere.cpp, we don't need to modify the header files. We come down, this is the code that we modified here in the previous episode, if you've seen that, and this is the new code. So this is what we had originally, this code that I've commented out here, and you can see this is the method I used to take into account translations when I originally wrote this. So I declared a vector at the origin, and then I transformed that by applying the forward transform to give the new object origin, and then I used that as the basis to calculate the normal vector. And that works perfectly well, as we saw, for a uniform sphere. Okay, but it really starts to go wrong if you apply uneven scaling. What we're doing now instead, okay, so that's all commented out. What we're doing now instead is we simply extract the normal vector, which for a sphere, remember we're in our local coordinate system, so this is always a unit sphere at the origin. Okay, so the normal vector in that case is simply equal to the point of intersection. And then we use m_transform to apply norm, the new function that we wrote, okay, to apply the normal vector to normal vector, okay? And then we simply do local normal.normalize, and we're done. Okay, so looking at planes, again, we do exactly the same thing. So this is object plane.cpp, and if we scroll down, we see here this is the method we used originally. It's the same outline. We calculate the local origin, we transform that, and then we simply apply we have a predefined normal vector because we know what it's going to be. In the case of a plane, it's simply going to be pointing upwards, and we transform that and we normalize. But to do the new way, we define our normal vector there, which we know is simply going to be a vector pointing up. Again, because we're in our local coordinate system, that's really important to remember. In this case, we always have a plane that lies in the xy plane with its normal pointing in the upward z direction, which in our coordinate system is the negative z direction. And then we simply do local normal is equal to m transform matrix dot apply norm normal vector and normalize it, and there we go. You see, not only does this actually now work correctly, it's also a lot simpler to implement. Okay, let's look at another shape. So this is the code for cylinder.cpp, and now cylinders are more interesting because they have both the cylinder itself and the end cap. Okay, so here's the code to calculate the normal actually for the cylinder. Right, that shouldn't be commented out. Okay, so in this case I haven't actually commented out the original code. What we calculate is this variable called org_normal. And what I'm going to just comment that out. There we are. Of course, we don't need that. So org_normal is the vector that we have representing the normal in the original coordinate system. Oh, no. It's like that. There we go. Okay, a little bit confused. So in this case, we calculate the original normal in the original coordinate system, which we covered when we looked at how to do that. We covered when we looked at cylinders, so you can go back and look at the cones and cylinders episode if you want to know more about that. And then we simply do local normal as m transform matrix dot apply norm org normal, local normal dot normalize, and there we go. And this is the original code that we had there. I've just commented that out. Okay, also for cylinders, of course, we have the end caps, important to remember. So we have this code here to check the end caps. In this case, we have our original normal vectors defined this way. Again, we talked about that in the episode where I talked about cylinders, and then we simply apply the normal vector in exactly the same way. Okay, so let's have a look at cones. Cone.cpp, cones, exactly the same situation. If we come down to the bit where we actually calculate the normal, that's here. Okay, so we calculate the original normal here based on this. Again, we talked about that in the episode on cones and cylinders, and then we simply apply the normal vector m transform matrix dot apply norm and normalize. Okay, really very straightforward. And of course, we have to do the same for the end cap like we did. So we do that here. Here we go. Yep, this code here. So we have the local origin. We define our normal vector. It's simply defined like that, pointing downwards in the local coordinate system. And we simply apply norm as we've done before and normalize. And that's it. Okay, so that's all of the modifications that we've had to make to the code to make this work. So let's just go to the terminal window. Let's compile, run, and check that everything works as it should. Here we go. I'm at my terminal window and I'm in the project folder. If you've been following along with the project as we've been going through the episodes, you should have all of these files. If we look in the Qb Raytrace subfolder there, we have all of our files, Gtfn and so on, and then the shapes are in Qb primitives, everything else. So that's fine. Let's get rid of that. Let's just run make. Let's compile all of that code. I did a little bit of editing here on the video, so hopefully I haven't made any errors. That should just go through. There's quite a few files there now, but there we go. And if we run, okay, so let's see what we get. We should get the image similar to the one that I use for the thumbnail for this video. I'm going to look at performance for this ray tracer in an episode coming soon. I'm not sure exactly when, but I think we can probably make it go a lot faster than this with some tweaking. And there we go. So this is the result that we get. So this is the image that we've seen before with the glass ball. We've got the demonstration that we can do image textures. We've got the 3 reflective balls here, the reflective checker floor that's classic for all ray tracing demonstrations, or at least it used to be. And we have a cone here, nicely demonstrating that we do indeed now get the proper reflections in the surface of our cone, indicating that we have actually now calculated the normals correctly. And the illustrations at the beginning were all produced using the mathematics, exactly the code implemented in my in this ray tracer. So, you know, we do know that we are definitely now producing normals that are correct. So there we go. That's really everything that I wanted to talk about today. We've had a look at how we transform the normals, and we've looked at why we have to treat the normal vectors differently compared to vectors that are tangential to the surface, or indeed to points on the surface. We've looked at some of the maths, a little bit of the maths there behind that, and then we've gone on to show how that can be implemented in the ray tracer code so that we calculate the normals correctly. Okay, so I really hope that's been of interest, and I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't miss any future videos. Thank you very much. So moving on from here, we're going to continue, as I said at the beginning, looking at increasingly more and more advanced concepts. There's some other primitive shapes that we should look at implementing. That's probably what I'm going to do next, although I'm not 100% sure. So I'm going to look at things like boxes, and then I want to look at torus or donut shapes and that kind of thing. And then after that, I'm going to look on progressively more complicated things. Anyway, listen, it's really been a pleasure. I really hope you've enjoyed this video. It's been a great deal of pleasure making it, and I really look forward to seeing you in the next one. Thank you very much for watching. Bye.